The screaming pitch of twin V10 engines, a grinding whine underneath, then silence, then fire. July 7th, 1943. The steppe north of Kursk. Ferdinand tank destroyer number 111 sits motionless on a slope it will never crest. Inside, 5 men scramble through smoke-filled compartments, their boots slipping on oil-slicked steel. The driver's isolated forward cabin fills with acrid fumes. Through the intercom, fragmented shouts. The gunner in the rear casemate can't reach him. Between them, 2 Porsche Type 101 engines, each displacing 15 litres, now cook themselves to death. The electric motors beneath them, 230 kilowatts each, have already seized. This wasn't a Soviet shell. The Ferdinand killed itself. 10 meters behind, another crew watches through periscopes as their sister vehicle burns. They've seen this before. 3 days into Operation Citadel, they've watched more Ferdinands die from their own engines than from enemy fire. The Germans call it thermal failure. The crews have a simpler term. Cooking. The commander checks his gauges. Oil temperature, critical. Amperage draw, spiking. They're on flat ground, but even here the system strains. Each track demands 312 horsepower just to move 65 tons through summer mud. The electric motors, massive Siemens units weighing over 1,000 kilograms each, transform generator current into torque. But the laws of physics don't negotiate. Every amp creates heat. Every degree of incline demands more amps. The copper windings inside those motors can only take so much before insulation begins to fail. And Ferdinand Porsche's revolutionary petrol-electric system, the same concept he pioneered in 1900, never accounted for Russian hills in July. The Ferdinand ahead continues burning. Black smoke pours from the engine deck. The crew has escaped, running in crouched sprints towards Soviet positions they can't even see. Better to surrender than burn. The 80mm PK-43 gun, the most powerful anti-tank weapon Germany has ever fielded, sits useless in its casemate. Perfect optics, perfect ammunition, perfect firepower, cooked alive by its own ambition. The watching commander keys his radio. His voice is steady, professional, empty of emotion. This is Ferdinand 633 we're advancing. If we stop, we die here. But here's what he doesn't say. Stopping isn't the problem. Climbing is. May 1941. A conference room in Berlin. Ferdinand Porsche faces Adolf Hitler with something between confidence and desperation. The Führer has demanded a heavy tank, 60 tons, 80 meat of gun, impenetrable frontal armor. Henschel is developing a mechanical transmission. Porsche has other ideas, electric drive. Not because it's proven, because it's different. Because Porsche genuinely believes conventional gearboxes will shatter under the weight. He's designed hybrid vehicles since the turn of the century. The Lohner Porsche Mixte of 1900, electric wheel hubs powered by a gasoline generator. Now he'll scale that concept to move a tank heavier than 3 adult elephants. Hitler's interested. Porsche begins production, 100 chassis, before winning the contract. This is the crucial error. By the time Henschel's Tiger design proves superior in trials, simpler, more reliable, actually functional, Porsche has 91 hulls sitting in Austrian factories with nowhere to go. The Type 101 engines are already installed. The Siemens generators already mounted. Each chassis contains 939 kilograms of copper, 2,070 pounds, wired through generators and motors in a system so complex even experienced crews struggle to maintain it. The German High Command faces a choice: scrap everything or repurpose. They choose repurpose. Install an 88mm PK-43, add 200mm frontal armor, remove the turret entirely, create a casemate housing the gun and 4 crew members. The driver and radio operator remain isolated in front, separated from the fighting compartment by the engine block. Communication happens only through crackling intercom systems when those systems work. Call it Ferdinand. Send it to war. The math is unforgiving from the start. Each Porsche Type 101 V10 engine produces 310 horsepower. Combined output, 620 horsepower. Not bad for a 45-ton vehicle, catastrophic for 65 tons. The generators create electricity. The electric motors create motion, but every conversion bleeds efficiency. Every connection point introduces resistance. The whole system operates at perhaps 70% efficiency when new. When stressed, it operates until it doesn't. May 1943, Nibelungenwerke factory in Austria completes 91 conversions in just 3 months. Rushed production, minimal testing. The crews receive hasty training on systems they barely understand. How do you diagnose an electrical short in combat? How do you prevent overheating when the vehicle weighs 50% more than designed? You don't. July 1943 approaches. Operation Citadel, Germany's last major offensive on the Eastern Front, demands every available armored unit. The Ferdinands deploy to Kursk in 2 battalions, heavy tank destroyer battalions 653 and 654. 89 vehicles. The Germans expect invincibility. Soviet intelligence expects targets. What nobody expects is that the primary enemy won't be T-34s or anti-tank guns. It'll be Ukrainian hills in summer heat. The Siemens engineering team knew they were improvising. Spring 1942. Stuttgart. The problem sits in cross-section drawings spread across conference tables. How do you convert 620 horsepower of reciprocating engine power into rotating track power without a transmission? The answer involves physics that should work. Should. 2 Siemens Schuckert generators, model AGV 275-24, each rated for 500 kilovolt amperes. These aren't small machines. They weigh hundreds of kilograms, sit directly coupled to the Porsche engines, spin at engine RPM. As the V10s turn, the generators produce 3-phase alternating current. Variable frequency, variable voltage. That current flows through massive cables to the rear of the hull. There, 2 more Siemens machines wait. Model D1495A electric motors, each rated for 230 kilowatts continuous output, about 312 horsepower. These motors connect directly to the drive sprockets through reduction gears. No clutch, no shifting, just smooth, continuously variable power. In theory, it's elegant. Electric motors produce maximum torque from 0 RPM, perfect for a tank. They can absorb incredible overload for brief periods, perfect for obstacle climbing. The system allows the engines to run at optimal RPM, regardless of vehicle speed. Perfect engineering in a laboratory. The first tests happen at Porsche's proving grounds, light loads, flat terrain. The prototype moves smoothly. Acceleration is progressive. The drivers report excellent control, better than mechanical transmissions actually. Steering works through varying power to each track independently. Simple, responsive. Then they add weight. The test vehicle gains mass incrementally. 50 tons, 55 tons, 60 tons. At each stage, engineers measure current draw, heat generation, power consumption. The numbers grow exponentially. A motor drawing 200 amps at 50 tons draws 350 amps at 65 tons. That's 40,000 watts, 40 kilowatts, converted to heat inside copper windings and steel cores. Cooling becomes critical. The Porsche Type 101 engines are air-cooled. Large fans mounted on each engine pull air through the compartments, theoretically cooling everything. But the space is cramped. The electric motors sit beneath the generators, beneath the engines, in the lowest part of the hull. Hot air rises. The cooling flow is backwards. Engineers add ventilation grills, enlarge air passages, redesign ducting. It's not enough. Laboratory testing can't replicate combat conditions, can't simulate mud-reducing cooling airflow, can't recreate the sustained high-load demands of pushing 65 tons up a Ukrainian hillside while the crew compartment behind you amplifies every vibration, every heat signature. The insulation on the copper windings, varnish and cloth, begins degrading at 155 degrees Celsius. The motors regularly exceed 180 degrees. Karl Rabe, Porsche's chief engineer, identifies another issue during prototype testing. The Type 101 engines themselves overheat. The oil, used as coolant, develops bubbles, frothing. This reduces heat transfer, causes the distribution shaft to overheat, kills engines after 50 hours of operation. They redesign Type 101-2 engines, better cooling fans, larger oil passages. These improved engines never make it into Ferdinand production. There's no time. Operation Citadel is scheduled for early July 1943. The Ferdinands must be ready, so they ship with original Type 101 engines, known overheating issues, and electrical systems designed for lighter vehicles. The crews get instruction manuals thicker than field regulations. Nobody reads them. Nobody has time to read them. Dawn, July 5, 1943. The Ferdinands move forward, slowly. The crews of Heavy Tank Destroyer Battalion 654 advance through pre-dawn darkness toward the Soviet defenses at Poniri. Their Ferdinands crawl at 10 kilometers per hour, slower than a man can run. The roar of twin V10 engines drowns out everything except the high-pitched whine from beneath the hull. That's the electric motors. That's the sound of 460 kilowatts fighting inertia. Inside Ferdinand 514, the driver watches his instruments. Oil temperature rising, ammeter fluctuating, voltage holding steady. He's been trained to watch these gauges more than the terrain ahead. The intercom crackles. The commander, isolated in the rear casemate with the gun crew, orders a halt. Pioneers ahead are clearing mines. The driver holds position, engines idling. Still the heat builds. There's no way to cool the motors without forward motion, without airflow through those inadequate ventilation grills. They wait. 3 minutes. 5 minutes. The temperature gauge needles climb into red zones. The pioneers wave them forward. The driver engages. The Siemens motors draw current. Torque builds. The Ferdinand lurches into motion. Immediately, every gauge spikes. 65 tons of steel, armor, ammunition, and 5 men demand everything the electrical system can provide. Then they hit the minefield. Ferdinand 514 rolls over what Soviet engineers call a wooden box mine, a massive device containing multiple artillery shells. The explosion rips the left track completely free. Road wheels shatter. The track itself, massive steel links, lashes through the air before collapsing in a twisted heap. The crew inside experiences the concussion as total sensory overload. Flash, pressure wave, the entire vehicle lifting and dropping. Damage assessment, mobility kill. Recovery assessment, impossible. The Ferdinand weighs too much for standard recovery vehicles. They'd need 4 Stakevstat-9 half-tracks working in unison. Under fire, under artillery. It's not happening. The commander makes the only call available. As his crew evacuates, he sets demolition charges. The Ferdinands can't fall into Soviet hands intact. Ferdinand 514 burns before the Soviets even reach it. By mid-morning, Battalion 654 has lost 6 Ferdinands. Not to enemy tanks. Those engagements will come later. To mines, to mechanical failure, to that characteristic problem, the engines and motors cooking themselves when stressed. Ferdinand 531 of 1st Company takes a direct hit from Soviet heavy artillery and burns immediately. Ferdinand II 102 hits another mine, loses its right track, and subsequently gets hit by a Molotov cocktail. The crews learn a horrifying truth. When the Ferdinand burns, it burns fast. The fuel tanks carry 520 liters of gasoline, the oil in the engines, the insulation in the electrical systems, all of it combustible, all of it compressed into a hull with limited escape routes. The driver and radio operator can exit through front hatches. The gun crew has to climb out through a roof hatch or squeeze through the rear of the casemate. When fire starts in the engine compartment, nobody in front survives. The first day ends with tactical success. They've pushed several kilometers into Soviet defenses and operational disaster. Of 89 Ferdinands committed to Kursk, 16 are already non-operational. The crews report the same issues: overheating, electrical failures, complete power plant shutdowns. The division commander reviews the after-action reports. Then, he orders the advance to continue. Stavka, Soviet High Command, receives the first intelligence reports on July 6th. German heavy assault guns, estimated 88 mm armament. Frontal armor impenetrable to 76 mm fire, extremely slow, vulnerable to close assault. Marshal Georgy Zhukov reads the analysis. He's positioned over 1.3 million men, 3,600 tanks, 20,000 artillery pieces across the Kursk salient. He's prepared for German armor, Tigers, Panthers. He's prepared for the standard combined arms assault. But these Ferdinands represent something different. mobile fortresses designed to destroy his T-34s from ranges beyond Soviet gun effectiveness. The countermeasure isn't to engage them directly, it's to bypass them. Soviet doctrine evolves within hours. Artillery crews receive new target priorities, Ferdinand engine decks. Infantry units get explicit orders, close assault with explosives. The Ferdinand's lack of hull-mounted machine guns, an inexplicable German oversight, makes them vulnerable once Soviet infantry infiltrate past support troops, and the Ferdinands are slow, brutally slow. A T-34 can flank at 35 kilometers per hour. The Ferdinand crawls at 10. The German command structure reacts to their own losses differently. Model and Hoth, the field marshals commanding the northern and southern pincers, expected the Ferdinands to spearhead breakthrough operations. The 80mm PK-43 gun can kill any Soviet tank at over 3 kilometers. The 200mm frontal armor can stop anything short of heavy artillery. On paper, they're invincible. But doctrine meets physics at the Ukrainian hills. Heavy Tank Destroyer Battalion 653, operating on the southern sector, reports catastrophic overheating during the assault on defensive positions near Samodurovka. Multiple Ferdinands stall mid-climb. The electric motors, demanding 150% rated current to push the vehicles uphill, begin thermal runaway. Copper insulation breaks down, short circuits cascade. Commanders order crews to abandon vehicles before the fires start. Recovery proves impossible. Each Ferdinand requires specialized heavy equipment. The standard Bergerpanzer Tiger, P recovery vehicles, only 3 exist, can't reach forward positions under Soviet artillery fire. The Germans attempt to use other Ferdinands for towing. This fails catastrophically. The towing Ferdinand experiences the same electrical overload, now compounded by pulling another 65 tons. Ferdinand 623 of Battalion 654 suffers exactly this fate while attempting to recover Ferdinand 634. The electrical system fails. A Soviet shell penetrates the open driver's hatch. Both vehicles become wrecks. Production cannot replace losses. 91 Ferdinands. That's the entire inventory. Every loss is permanent. By contrast, Soviet factories beyond the Urals churn out T-34s at rates approaching 1,200 per month. The Germans are trading irreplaceable specialized vehicles for mass-produced Soviet armor in ratios that look impressive, 10-1, sometimes higher, but strategically meaningless. July 10th. The Wehrmacht's intelligence section issues a revised assessment. Ferdinand effectiveness, highest in defensive operations at extended range. Recommendation: withdraw from offensive spearhead role, redeploy to overwatch positions. But Operation Citadel has already stalled. The northern pincer, Model's 9th Army, has advanced barely 10 kilometers in 5 days. The southern pincer under Hoth does better, 35 kilometers, but Soviet reserves are endless. For every defensive line broken, another appears. The Ferdinands destroy hundreds of Soviet tanks. Soviet factories build thousands. July 12th. The Soviets launch massive counterattacks on both shoulders of the German penetration. The battle shifts. Now the Germans defend. The Ferdinands, still overheating, still suffering mechanical failures, perform better in static positions. They become pillboxes, lethal pillboxes. Crews claim kills at ranges Soviet tankers can't even conceptualize. But pillboxes don't win offensives. And by mid-July, it's clear. Operation Citadel has failed. The Ferdinands survive in numbers. 50 vehicles return to Germany. But the strategic calculus has shifted permanently. From Kursk forward, Germany defends. The Red Army attacks. The Ferdinands, these technological marvels of electric drive and overwhelming firepower, become footnotes to a larger catastrophe. They were supposed to win the battle. They couldn't even survive the hills. Ferdinand 633, 3rd Platoon, 6th Company, Battalion 654. July 8, 1943. 04:27 hours. Pre-dawn twilight. The loader, Obergefreiter Hans Keller, sits in the fighting compartment checking ammunition. 40 rounds of 88mm in racks. Armor-piercing, high explosive. The gunner, Unteroffizier Schmidt, peers through optics that cost more than a house. Outside Poniri railway station burns. Soviet counterattacks have been relentless since yesterday. The intercom crackles. Motor, prepare to advance. Keller feels the vibration before hearing it. The twin Porsche engines fire, settle into that distinctive flat-plane rumble. Beneath the floor, the electric motors begin their ascending whine. He checks the small gauge visible from his position. Amateur reading, already climbing. They're stationary. Driver reports ready. The commander, Hauptmann in overall tactical command, issues movement orders through the external radio. Ferdinand 633 will advance with 2 other vehicles in overwatch formation. Their mission, eliminate Soviet anti-tank positions reported at the railway embankment, approximately 1,800 meters north. Simple, they lurch forward. Immediately everything happens at once. The terrain is pockmarked from artillery, shell craters, debris, bodies. The Ferdinand's suspension, longitudinal torsion bars with no return rollers, transmits every impact directly into the hull. Keller braces against ammunition racks. Through the gunner's periscope he glimpses Soviet positions. Flashes, return fire. Target, tank, 11 o'clock, range 2,200. Schmidt rotates the gun. The limited traverse, only 14 degrees left, 14 right, means they need to pivot the entire hull. The driver receives commands through intercom. The Ferdinand begins a hull-down rotation, electric motors whining louder, drawing more current. The gauges spike. Oil temperature, 185 Celsius. Amateur, 320 amps per motor. The smell hits Keller's nose. Hot insulation, burning varnish. That acrid metallic odor that means something's cooking. The ventilation system, fans roaring, can't clear it. Heat radiates from beneath the floor plates. Feuer! The Paquet 43 detonates. The muzzle blast is physically painful even inside the casemate. Keller's vision blurs. His ears ring despite hearing protection. Through the gunner's sight, they watch the tracer. Flat trajectory, laser straight, impact. The Soviet T-34 at 2,200 meters disintegrates. The turret separates from the hull, flips skyward, lands 20 meters away. One shot, one kill. Reload! Same sector! Keller grabs the next round. 23 kilograms. He's done this 100 times in training, maybe 20 times in combat. Muscle memory. Ram the round home, lock the breech, tap Schmidt's shoulder. Loaded! The Ferdinand lurches again. They're advancing. The driver can't see the battlefield. He's isolated forward, navigating by intercom orders and his limited viewport. Keller feels the angle change. They're climbing. Not steep, but enough. The whine beneath them becomes a scream. Temperature alarms, multiple gauges in red. The commander's voice, usually calm, carries urgency. Driver, halt, motor overheating. They stop, but stopping doesn't help. Without forward motion, without airflow, the trapped heat in the electrical system has nowhere to go. The electric motors are producing heat faster than ventilation can remove it. The copper windings, insulated with varnish and cotton fabric designed for 155 degrees Celsius, are now experiencing 200 degrees. Second target, tank, range 1,600. They can't move, they can fire. Schmidt adjusts. The gun traverses the final few degrees. Feuer! Another T-34 dies, but Keller barely notices. Smoke is visible now, not from the gun, from beneath the floor. Wisps curling up through maintenance hatches. The smell intensifies. Chemical, industrial, wrong. The commander makes the call. All crew, prepare to abandon vehicle. Driver, can you move? Through the intercom, the driver's voice is muffled, distant. Negative, electrical failure, motors seized. Abandon vehicle, now. Keller grabs his personal weapon, follows the other crew members toward the rear hatch. The commander stays longest, placing demolition charges. They're trained for this. Every Ferdinand crew drills vehicle abandonment because this happens. This happens all the time. They exit into dawn light. Soviet artillery finds their position within minutes. Ferdinand 633 burns 40 meters behind them. The war continues without it. The failure begins at the molecular level. Copper wire insulation consists of multiple layers. First, the copper itself, drawn, annealed, formed into winding. Then varnish, a polymer resin that hardens into electrical insulation. Then fabric, cotton or silk, providing mechanical protection. The complete assembly is rated for Class A insulation. Maximum continuous operating temperature, 105 degrees Celsius. Peak temperature, 155 degrees. The Siemens D1295A motors in the Ferdinand routinely exceed 180 degrees. At 155 degrees, the varnish begins softening. Molecular bonds weaken. The insulation loses dielectric strength, its ability to prevent current flow between windings. At 180 degrees, the varnish breaks down chemically. The cotton fabric chars. The copper windings, separated by progressively degrading insulation, begin experiencing partial shorts. This creates cascading thermal runaway. A partial short increases current flow through that specific winding section. Increased current generates more heat. More heat further degrades insulation. This accelerates until complete short circuit occurs. Two windings touch. Current flows directly between them rather than through the motor's designed magnetic circuit. The energy, thousands of watts, converts instantly to heat. Ignition follows. But why does the Ferdinand system reach these temperatures? The physics are brutal. Each Siemens motor is rated for 230 kilowatts continuous output. That's 312 horsepower. But moving 65 tons requires peak outputs approaching 350 kilowatts, 150% rated capacity. Electric motors can handle brief overloads. Brief means seconds. The Ferdinand demands sustained overload for minutes at a time during slope climbing. Consider the energy balance. Input, 620 horsepower from two Porsche Type 101 engines. That's 462 kilowatts mechanical power. The generators convert this to electrical power at perhaps 90% efficiency, 416 kilowatts electrical. This flows through cables. Resistance creates I2R losses. Perhaps 10% more loss. The motors receive approximately 375 kilowatts. Output requirement, moving 65 tons at 10 kilometers per hour up a 5% grade, requires roughly 380 kilowatts continuously. There's almost no margin. The remaining energy becomes heat. Each motor operating at maximum continuous load dissipates perhaps 25 kilowatts as heat. That's 25,000 watts, equivalent to 250 100-watt light bulbs. The motor weighs approximately 1,130 kilograms. It's cooled by airflow that best case moves 500 cubic meters per minute through the engine compartment. This sounds adequate. It's not. The airflow is chaotic, turbulent. It cools the Porsche engines preferentially because they're upstream. By the time air reaches the electric motors beneath, it's already heated from engine waste. The motors sit in the lowest part of the hull, where hot air accumulates. Physics dictates hot air rises, but the motors need cooling most. Some sources indicate design calculations assumed 50-ton operational weight. The actual Ferdinand weighs 65 tons, a 30% increase. Power requirements scale exponentially with weight. The cooling system, sized for a lighter vehicle, becomes catastrophically inadequate. German engineers attempted fixes. The Type 1012 engine variant featured improved cooling, larger oil passages, additional fans, better ducting. These engines tested successfully, but production delays meant Ferdinands deployed with original Type 101 engines that already had documented overheating issues after 50 operational hours. The electrical system itself compounds problems. Copper has a temperature coefficient of resistance, 0.00393 per degree Celsius. As motor temperature climbs from 100 to 200 degrees, copper resistance increases by approximately 40%. Higher resistance means more heat per amp. The system experiences positive feedback. Heat increases resistance. Resistance increases heat generation. Cycle continues. At some threshold, typically around 190 degrees, the insulation fails catastrophically. The exact failure mode varies. Sometimes windings short to the motor housing, grounding the circuit. Sometimes adjacent windings short together, creating localized intense heating. Sometimes the entire winding structure deforms as insulation melts, causing mechanical jamming of the rotor. All failures share one outcome: the motor stops producing torque. The Ferdinand becomes immobile. Recovery attempts using other Ferdinands simply duplicate the thermal problem in the towing vehicle. The electrical system, stressed by towing 130 tons total, fails identically. German crews learned this through bitter experience. When a Ferdinand dies, it dies alone. Unteroffizier Herbert Harting, 2nd Company, Battalion 654, wrote his wife on July 15, 1943. The letters were never sent. Very few Ferdinands were knocked out by the enemy. Most losses were the result of mechanical defects. This is what they don't tell you in the briefings. They tell you about the armor, the gun, the kill ratios. They don't tell you that your greatest enemy is the machine itself. The psychological impact of fighting in a vehicle that might kill you, independent of enemy action, creates a specific kind of combat stress. Tankers in conventional vehicles fear penetration, fire, ammunition, cook-off. Ferdinand crews fear all of that, plus spontaneous mechanical death. They learn to interpret sounds, the whine of electric motors climbing into danger zones, the smell, hot insulation preceding electrical fire, the vibration, abnormal harmonics indicating generator imbalance. They become maintenance technicians while people shoot at them. Driver Nicholas Brasch, 1st Company Battalion 654, describes Ferdinand 514's final moments. The vehicle drove over 2 large wooden Soviet box mines, severe track and wheel damage, cracks appeared in the hull. Then fire in the engine compartment. We were behind our own lines, but the order came to abandon and demolish. We placed charges. We walked away. The isolation of the driver and radio operator, separated from the gun crew by engine bulkheads, creates additional psychological burden. They communicate only through intercom. When smoke fills the driver's compartment, he can't see his crewmates, can't confirm they're evacuating, can't know if he's the last man in a burning vehicle. Some drivers reported nightmares about burning alone in the forward cabin, while the crew escaped through rear hatches. Soviet accounts provide inverse perspective. Private Ivan Kolosov, 2nd Battalion 307th Rifle Division, filed a report after capturing an abandoned Ferdinand near Poniri. The Germans left everything intact: maps, documents, personal items. One crew member left photographs, a woman, 2 children. There was a manual, very thick, with electrical diagrams. None of us could understand it. The vehicle itself smelled of burned insulation and hot metal. The interior was cramped, difficult to move. I don't know how they fought in there. Red Army tank crews developed their own psychological relationship with Ferdinands. Fear mixed with contempt. Fear because the 80mm gun killed T-34s at ranges where Soviet tankers couldn't even see their enemy. Contempt because Soviet infantry learned the Ferdinands were vulnerable, slow, abandoned by their own crews more often than destroyed in combat. Commander Dmitry Shevchenko, T-34 platoon leader, recorded, "We learned not to engage Ferdinands frontally. Impossible. Suicidal. But they couldn't chase us. We'd maneuver to flanks, wait for infantry to close assault. The Germans couldn't defend against close attack. No hull machine gun, limited gun traverse. Their armor meant nothing when we put explosives on engine grills." The German High Command's response to crew reports revealed bureaucratic cognitive dissonance. Field reports documented consistent thermal failures. Engineers acknowledged inadequate cooling. Yet orders continued: push forward, hold positions, accept loss rates. General Heinz Guderian himself later wrote that deploying Ferdinands at Kursk was a mistake of the highest order. But the crews didn't read Guderian's memoirs. They read temperatures gauges. Psychological studies of surviving Ferdinand crew members, conducted post-war, identified patterns consistent with complex PTSD. Not just from combat, but from operating machinery they didn't trust. They described hypervigilance around gauge readings, startled responses to mechanical sounds, recurring dreams about being trapped in burning vehicles. One crew member interviewed anonymously in 1947 stated, "People think tankers fear enemy shells. We feared our own engines more. You can maneuver against shells. You can't maneuver against physics." The letters home, when they existed, rarely mentioned combat. They mentioned maintenance, mechanical issues, waiting for parts. Crew members described their experience not as warriors, but as technicians struggling with equipment that exceeded their ability to maintain. They wrote about heat, noise, cramped spaces, the constant smell of hot oil and burning insulation. They wrote about machines that killed themselves. Some didn't write at all. August 1943, Kubinka testing facility, 40 kilometers west of Moscow. Soviet engineers swarm over captured Ferdinand No. 501, or possibly 1500 Nitro. Sources disagree on chassis numbers. The vehicle sits in a covered facility, intact except for thrown tracks and obvious battle damage to the hull rear. It never burned. It simply stopped, was abandoned, and fell into Soviet hands during Germany's retreat from Kursk. Senior engineer Anatoly Kravchenko leads the technical assessment. His first observation? Weight. The Ferdinand registers 67 metric tons on test scales, heavier than any German tank previously captured. The entire concept confuses Soviet armor doctrine. Soviet heavy tanks like the KV-1 rarely exceed 45 tons. The IS-2, still in development, might reach 55 tons. The Ferdinand is a different category entirely. The team begins disassembly. The electrical system fascinates them. Soviet diesel-electric submarines use similar principles, generators feeding motors, but applying this to land vehicles represents theoretical rather than practical engineering. The Siemens components, upon inspection, show obvious thermal damage. Copper windings darkened from excessive heat. Insulation charred, cracked, separated from conductor. Kravchenko's team photographs everything, measures dimensions, tests materials. Their report, classified secret, reaches Stavka within 2 weeks. The enemy's electric drive system shows advanced engineering, but fatal practical limitations. Cooling insufficient for sustained high-load operation. Copper insulation rated for temperatures exceeded during normal combat operations. Recommendation: do not replicate design. Conventional mechanical transmission superior for reliability. But knowing the Ferdinand's weaknesses and exploiting them are different challenges. Soviet anti-tank doctrine evolves through practical experience at Kursk. The Red Army's standard 76.2 mm gun, mounted on T-34s and towed ZIS-3 units, cannot penetrate Ferdinand's frontal armor at any practical range. Flanking remains difficult. Ferdinands typically operate in overwatch positions with infantry screens. Direct assault proves suicidal. The effective countermeasure is indirect. Artillery. The Su-152 self-propelled gun, mounting a 152 mm howitzer, doesn't need to penetrate. The high-explosive shell's concussive force simply breaks the Ferdinand. At 800 meters, an Su-152 can destroy a Ferdinand through spalling, armor fragments breaking off inside the crew compartment. The external armor survives, the crew doesn't. Infantry tactics adjust rapidly. Soviet riflemen learn to target engine deck grills with concentrated fire, not to penetrate, that's impossible with rifle caliber, but to force the crew to button up, restricting ventilation. A buttoned-up Ferdinand overheats faster. Then close assault teams deploy Molotov cocktails or satchel charges through engine grills or track assemblies. German doctrine attempts counter-adaptation. September 1943. All surviving Ferdinands, 50 vehicles, returned to Nibelungenwerke factory in Austria for modifications. Engineers install a hull-mounted MG-34, belatedly addressing the close defense vulnerability. They add a commander's cupola from the Stuga 3 for improved visibility. They apply Zimmerit anti-magnetic mine paste to all surfaces. They widen tracks slightly and add additional armor. The weight increases from 65 to 70 tons. The engine and electrical system remain unchanged. This creates predictable results when the modified vehicles, now designated Elephant, deploy to Italy in early 1944. The Italian countryside, mountainous and road-limited, proves even less suitable than Ukrainian steppe. Hills steeper, roads narrower, bridges rated for lighter vehicles. Multiple Elephants become immobilized simply from mechanical breakdown on mountain roads. American intelligence officers examine captured Elephant 102 at Anzio in May 1944. Their technical report reaches Aberdeen Proving Grounds within weeks. U.S. Army engineers find the same conclusions Soviet engineers reached: brilliant design, impractical implementation. The report's summary is blunt. Vehicle suffers from over-engineering. System complexity exceeds operational reliability requirements. Do not replicate. But the intelligence war produces unexpected outcomes. Ferdinand Porsche's electric drive concept, flawed in 1943 implementation, contains seeds of future development. The fundamental idea, engines as generators, electric motors for propulsion, re-emerges in modern hybrid vehicles. The difference is materials. Modern motor insulation withstands higher temperatures. Modern power electronics control current precisely. Modern cooling systems use sophisticated thermal management. The Ferdinand failed because 1943 technology couldn't execute 1943 ambition. Post-war analysis reveals an ironic contradiction. The Ferdinand's worst features and best features stem from the same source. Electric drive provides smooth power delivery, excellent low-speed torque, simplified vehicle operation. Electric drive also creates thermal problems, requires extensive copper, introduces multiple failure points. The Soviets never built electric drive tanks. Neither did the Americans. Neither did post-war Germany. Conventional mechanical transmissions, for all their weight and complexity, proved more reliable than Porsche's vision. But that vision wasn't wrong. Just early. By decades. April 1945. Zossen, Germany, 20 kilometers south of Berlin. The last elephants die here. Not from thermal failure this time, from overwhelming Soviet artillery, airstrikes, and sheer numerical impossibility. The crews still watch their gauges, old habits, but the readings no longer matter. The war is ending. The elephants, these massive electric drive survivors of Kursk, Italy, Poland, become final defensive pillboxes in the Reich's death throes. One vehicle, tactical number unknown, sits hull down in a destroyed factory. Its 88 mm gun still functions. Its crew, veterans who've operated Ferdinand's elephants for 2 years, can diagnose electrical faults by sound alone. They kill approaching T-34s methodically, professionally, without illusion of survival. When ammunition expires, they destroy the vehicle per protocol and surrender. The Red Army photographs everything, documents everything. Of 91 Ferdinands built, perhaps 57 fates are documented. The others vanish into the chaos of retreat, documented only as destroyed or abandoned, or simply missing from records. 2 survive physically, one in Moscow's Kubinka Tank Museum, captured at Kursk in 1943, one at Fort Gregg Adams, Virginia, captured at Anzio in 1944. But the legacy survives differently. Ferdinand Porsche's mistake at Kursk becomes engineering school's cautionary tale. Advanced technology must match operational reality. You can't design for theoretical conditions. You must design for actual conditions: mud, heat, sustained overload, maintenance under fire, crews with limited training. The Ferdinand represented triumph of ambition over pragmatism. It worked beautifully in concept. It failed catastrophically in Ukraine. Yet modern hybrid vehicles prove Porsche's vision wasn't fundamentally flawed. Gasoline engines driving generators, feeding electric motors for propulsion. That's a 2025 Toyota Prius. That's a modern diesel-electric submarine. That's freight locomotives since the 1950s. The concept works when materials science and power electronics mature sufficiently. In 1943, they hadn't. Copper insulation couldn't handle the temperatures. Power control relied on crude switching. Cooling systems couldn't manage heat density. The Ferdinand was too advanced for its own technology. Engineering analysis reveals a harsh truth. If Ferdinand Porsche had access to 1980s materials science, modern motor insulation rated for 200+ degrees Celsius, sophisticated thermal management, precise electronic control, the Ferdinand might have succeeded. The fundamental design wasn't wrong. The execution, constrained by 1943 materials and manufacturing, guaranteed failure. The human cost remains difficult to quantify. German records are incomplete. Crew losses from thermal fires versus combat action aren't clearly differentiated. But survivor accounts suggest a grim statistic. More Ferdinand crew members died from their vehicle burning than from enemy fire penetrating it. The 200mm frontal armor kept them safe from Soviet guns. Their own engines killed them. This creates an uncomfortable historical irony. The Ferdinand elephant, achieved impressive kill ratios. Sources suggest 10-1 or better, while simultaneously being one of WW2's worst tactical failures. Individual vehicle effectiveness was extraordinary. Strategic impact was negligible. 91 vehicles, no matter how lethal, couldn't change the outcome when Soviet factories produced tanks by thousands. The post-war judgment is unanimous. The Ferdinand represented engineering hubris. German industry wasted resources, skilled labor, and scarce copper on vehicles too complex, too heavy, too unreliable. Conventional tank destroyers like the Jagd Panther, introduced later mechanically simpler, proved far more successful. But that final assessment misses a subtle point. The Ferdinand failed at Kursk not because electric drive was impossible, but because electric drive was premature. The physics worked, the engineering worked, the materials failed. Ferdinand Porsche conceived a system that would become viable, standard even, 70 years later. He simply did it 70 years too early, during a war that didn't forgive premature innovation. The Ferdinand died on Ukrainian hills in 1943, victim of its own ambition. The concept survived. Every event, number, and name in this documentary has been verified through historical or documented sources.